So in the last video, I talked about the original rope architecture. I talked about the input, the outputs, the belief map, affinity maps in here, and how loss is calculated for belief maps and affinity maps, and how we sort of the original author sort of used gradient injection to train the neural network, and it's an about 92 layer convolution, 92 layer deep convolutional neural networks. Now I'm going to propose my first modification to the network, which I call dope 2. So the main difference, as you can see quite evidently in here, instead of having two chains of cascades, now we have only one chain for calculating both belief maps and affinity maps. So a single chain will do both the jobs. That's my first proposal, that I will eliminate this part, this part, and I will use this chain only to calculate both the belief maps and the affinity maps. Okay, so I'll go into more details now. So again, just like previously, it gets W by H by 3 size input image, then goes to 10 convolution layers and 2 extra convolution layers, just like before. Then we end up with 128 channels of input feature maps, each of size W by 8, H by 8. Now we pass that around to my single chain system. This single chain will have uh, uh, 6 cascades just like before, but the difference is that now it will calculate both the belief maps and the affinity maps. So it's quite easy really. So if we look at the previous architecture in here, in the cascade one, let's see, it had 3 convolution layers of kernel size 3 by 3 by 128, then a single convolution layer of kernel size 1 by 1 by 512, and the final convolution layer would is just a is just a network in network style convolution. Is that it has a kernel size of 1 by 1 by 9. That is, it is basically just producing 9 belief maps. That's why the channel number is 9 in here. Similarly goes in here. We have the first 4 convolution layers in here, and then we have a kernel size of 1 by 1 by 16, which helps us produce the 16 leaf maps, affinity maps in here. Now my idea was that instead of using just 9 or just 16, let's calculate directly 25, and let's just get rid of this block. As a result, I would end up with 25 feature maps instead of 9 or 16, and I would take the first 9 of these feature maps as the belief maps and calculate my loss accordingly, and I will take the rest of the 16 feature maps as the affinity maps and calculate the loss accordingly. That's exactly what I did in here. So let's focus up in here for cascade 1. So again, just like before, the first 4 convolution layers, they come up with more nonlinearity in the feature maps. So eventually, up to this point, you end up with feature maps of W by 8, H by 8 by 512 channels. And then we use a convolution layer of kernel size 1 by 1 by 25, which basically converts this feature map of 512 channel to a feature to input feature of size W by 8, H by 8 by 25. Sorry, yeah, 25. So we are getting 25 images of W by 8, H by 8 size, and they are distributed in here, shown in here. Green represents again the belief maps, and 16 and the red represents the affinity maps. So we are getting 9 belief maps and 16 affinity maps. These are the 25 channel output. Same as before, in the cascade 2, we take as input the original input features of 128 channels. We are taking the previously calculated 9 belief maps, and we are also taking in the previously calculated 16 affinity maps. As a result, we are getting as input 153 input features, input feature channel, and then we calculate again the 25 feature maps, 9 for belief maps, 16 for affinity maps. Same goes for cascade 3, 9 and 16, cascade 4, 9 and 16, cascade 5, 9 and 16, and finally we are getting our 9 feature maps and 16 belief maps. And for loss calculation, just like before, now I have the loss calculation block in here, which takes as input all the belief maps and compare them with their ground truth versions. We also take the 16 affinity maps out of each cascade and compare them with the ground truth version of the affinity maps, and we end up with our final loss. And then we do the back propagation, and just like before, we do gradient injection towards each of these lines. As a result, we can train the neural network. Now let's just focus on the network a bit more. So let's count the number of convolutions, compare it with before. So just like before, in here we have 12 convolution layers. In here we have 5, 7, 7, 7, 7, 7. So now we end up with 12 plus 5 plus 35. That's 52. Yeah, I hope that do. Okay, so we end up with 52 convolution layers. So remember previously the number of convolution layers in total was 92. So in here what I'm saying is that I'm getting rid of about I'm getting rid of 40 convolution layers, and I'm trying to uh, make the convolutional this rope 2 architecture learn to do the same job more efficiently. That is, I'm trying to experiment whether I can use this reduced number of parameters, and can whether I can make them learn to use those parameters more efficiently than the original dope architecture. Or in other terms, can I use this reduced number of parameters to predict these belief maps and affinity maps just as accurately as this was calculating? My initial assumption is it won't be, but it won't be able to do it as accurately, definitely, because we are reducing the number of parameters. That means we are reducing the number of we are reducing the total capability of the neural network to learn to work with more non-linearity, but definitely we will see some speed ups, and I actually tested it with it it's about 1.5 times the speed up after the implementation. So this is the dope 2 architecture, and here I conclude my video about dope 2 architecture. Thank you for watching.